The 7 Dimensions of Reality. I have gradually arrived at the conclusion that reality is 7-dimensional. There are 3 dimensions of space, 1 dimension of time, and 3 dimensions of velocity space. For anyone who is struggling to understand what velocity space is, how velocity space works, or why velocity space is significant, this video may end up serving as a missing puzzle piece. I also hope to provide you, the viewer, with a new and more concrete understanding of relativity, and a new way of appreciating what it really means to say that all motion is relative. I also hope to convince you, the viewer, that the currently accepted notions of speed and inertial frame of reference are both wrong. I say that these conceptions are wrong because they're both inherently impractical and confusing. The most important idea in this video, and the core concept behind the supervelocity and selection theory of light, is the following definition of speed. Speed is defined as the distance between 2 points in velocity space. This is what I say is the correct definition of speed. Speed is the distance between 2 points in velocity space. However, this cannot be considered to be a new idea in the 21st century, because it's really just an articulation and an extension of well-established Galilean and Newtonian principles. We are standing on the shoulders of giants, and so I think it is important to take a moment to give credit where credit is due. It is natural to think that there are only 3 dimensions to reality, and if we consider time to also be a dimension, then it would also be natural to assume that there are only 4 dimensions. And this 4-dimensional paradigm was once a perfectly viable understanding of reality. That is, until these 4 giants of science revolutionized our understanding of space, time, and motion. You are looking at the 4 co-discoverers of velocity space. Galileo Galilei uncovered the notion of the relativity of motion, which corresponds to the idea that an inertial frame of reference can be construed as a point, and that a speed can be construed as a distance between 2 points in a 3-dimensional velocity space. Sir Isaac Newton came up with the idea of inertia, which corresponds to the idea that all objects have an inherent tendency to remain in the same fixed location in velocity space. Albert Einstein came up with the idea that the speed of observed light remains fixed in relation to the observer, but not in relation to the light source, which means that an observer can only see light that is found on the surface of a sphere in velocity space, with a radius that is equal to the speed of light, and that this sphere is centered around the observer, but not the source. And finally, Werner Heisenberg arrived at the idea that the more precisely we can determine the location of a particle in space, the less precisely we can determine its location in velocity space, and vice versa. The first founder of velocity space was Galileo Galilei, who proposed that all motion is relative. How far away is this object? In order for this question to make sense, then there must be an implied point of reference. How far away from what? One could ask a question like, how fast is this object moving? But in order for this question to make sense, then there must be an implied frame of reference. How fast relative to what? Galileo Galilei was the first to arrive at the idea that the laws of physics are the same in all inertial frames of reference. This idea is now known as Galilean relativity or Galilean invariance. In other words, all locations in velocity space are equal. Therefore, one cannot use the laws of motion in order to figure out where one is in velocity space. Another consequence of relativity is that there really is no such thing as how fast or in which direction any object is moving. An object can only be considered to move at some specific speed if we are measuring its speed in relation to some other object, or in relation to some observer, or in relation to some arbitrary inertial frame of reference. Galileo laid down most of the groundwork towards establishing a coherent concept of velocity space. The basic idea that all motion is relative motion actually comes from Galileo. But let's take some time out to delve a bit deeper into this idea. The idea that all motion is relative is actually a logical extension of an important spatial concept that we already understand on an intuitive level. A distance, for instance, is a straight line that connects 2 points. A distance is also a relationship between 2 points. Another way of stating this idea is to say that all distances in space are relative. In other words, a single object does not really have any particular distance. Rather, a distance is necessarily a relationship between two objects. Distances are also symmetric. If an acorn is 1 meter away from a pebble, then that pebble must also be 1 meter away from the acorn. We also recognize the fact that distances are symmetric intuitively. And we also understand intuitively that the distance between two objects has nothing to do with an arbitrary coordinate system that we impose on it from the outside. Nor does it depend on where an observer happens to be standing. To illustrate the invariant properties of a series of dots, objects, connected by lines, or distances, let's begin with a two-dimensional space with no time. What you see here is 7 points connected by 21 lines of different lengths. Because these lines all have different lengths, there are also 210 different ratios between the lengths of these 210 pairs of lines. Because these lines are also oriented in different directions, there are also 210 different angles formed between the 210 different pairs of lines. So we have straight lines which are connecting pairs of points to each other, and we have ratios and angles which connect pairs of straight lines to each other. That's quite a lot of concordance and agreement. This is actually an extremely stable, robust, and coherent system. It's objectively true that each point in this space really is where it is, and we have no choice in the matter of where it is. So what is my point in showing you this? Well, if we want to say where a point is, then we can just use the lines and the angles in order to objectively define its location, because the lines and angles are all invariant properties that belong to this particular configuration of points. We are not helplessly dependent on any arbitrary coordinate system. If you were to take just one of these points and move it, then the lines that are connected to it would also change their respective lengths and orientations. This would also change the ratios between the lengths of the lines and the angles between the lines. So in other words, the location of each point is actually defined by the ratios of the lengths of the lines and also by the angles between the lines. You cannot change one without also changing the other. All of these points in the network are mutually defined by the network. The location of each point is determined by the points themselves, not by us. I repeat, the location of each point is determined by the points themselves, not by us. What I've done here is I've demonstrated that there is already an endogenous coordinate system that is created by the points themselves. Each point has a well-defined location in relation to the constellation of other points. There's no need for us to impose any coordinate system on this set of points in order to specify where each of them is located. Each object is not just an object, but also a reference point for all of the other objects. The overall shape of this constellation of points will always be the same, no matter how we choose to describe their locations. The ratio between the lengths of the lines will not change, and neither will the angles between them. In economics, there's a similar distinction between nominal values and real values. You can say that you have $10, but really, this is just what you call what you have. If you want to know what the true value of what you have is, then you need to measure what your $10 can buy. That is the distinction between the nominal value of a currency and the real value of a currency. It doesn't really matter what we call it, what really matters is what we can do with it. And if we change what we call it, then that doesn't really change what it is. Inflation is a reduction in the real value of a currency relative to its nominal value. The kinds of coordinate systems that people construct tend to be simple and orderly, such as a grid made up of regular squares. We construct grid-like coordinate systems because these just make our lives easier. When constructing a man-made coordinate system, we can vary the scale of the grid lines or the units. We can also vary the orientation of the grid lines. And we can vary the location of the zero coordinates. To make this more concrete, let's say that these 7 points are real objects. Let's say that we have 7 islands. We can say that nature itself determines the location of each of these islands. Hence, the locations of these islands are objectively determined and fixed. These locations are not subjective or arbitrary, even though they are relative. The endogenous coordinate system is fixed and objective, while any human-constructed coordinate system would be arbitrary, subjective, and variable. What we have here is just 2 spatial dimensions and no time. But everything that I've just said would also apply to points, lines, and angles in a 3-dimensional space. So for example, the points could be a constellation of stars in the sky. To say that distance is relative is true because there really is no such thing as what the distance of an island is. Similarly, there is no such thing as which direction an island is in. Both the distance and the direction of an island will depend on which other island you are comparing that island to or viewing it from. However, this does not mean that the island has no objective position, nor does it mean that where an island is really is subjective or a mere matter of opinion or a matter of perspective. Each island really does have a real objective location regardless of which coordinate system we use and regardless of where it is being observed from. Each island has its own unique configuration of distances and angles which belongs specifically to it and ties it to all the other islands, almost like a fingerprint or a genetic code. The locations of each island are both objective and relative at the same time. And the endogenous coordinate system allows us to transcend subjectivity without making any arbitrary decisions. To see why these insights are profound and important, we'll need to take the exact same logic that we have just used to understand position and distance and apply it to velocity space. But first, I think that a brief recapitulation is in order. Number 1, a distance is never a property of a point. Number 2, a distance is always a relationship between 2 points. Number 3, a distance is a straight line connecting 2 points in space. Number 4, a distance is symmetric because the distance from A to B is equal to the distance from B to A. Number 5, the distance between 2 objects is independent from the coordinate system. Number 6, the distance between 2 objects is independent from where the observer is located. And number 7, the location of an observer is independent from the properties of the coordinate system. What Galileo essentially did is he extended this notion of relativity from distances in space to speeds in velocity space. All that a speed is a distance between 2 points in velocity space. That's it. There's really nothing more to it than that. Hence, Speed is relative in velocity space, just as distance is relative in space. Just as a distance is a property of a line, but not a point, a speed is a property of the relationship between two objects, but not of any particular object. Because a speed is just a distance between 2 points in velocity space, a speed must be symmetric as well. In other words, if one object is moving at 5 kilometers per hour relative to another object, then the second object must also be moving at 5 kilometers per hour relative to the first object. This is actually true, and it is very easy to confirm this idea with experiments. It is a very well established empirical fact that speed is symmetric, just as distance is. Because the location of a point is objectively determined and constrained by the entire network of lines connecting it with other points, their respective lengths, and the angles between these lines, this means that the location of a point in velocity space is also defined and constrained by its unique set of relationships to other points in velocity space. But how should we understand a point in velocity space? I have a somewhat careless habit of referring to a point in velocity space as a velocity. This is almost true, but not quite. It is better to think of a point in velocity space as an element or a component that is used to build a velocity. The length of the line that connects these 2 points is then the speed of the velocity vector, and the direction that the line is pointed in is then the direction of the velocity vector. An individual point in velocity space could be occupied by an inertial frame of reference, an observer, or an object. So long as a reference point in velocity space has already been selected, then all other points in velocity space would then correspond to velocities. We can also connect our abstract network of points in velocity space to real objects to make this more concrete. So for example, these points in velocity space could all represent the locations in velocity space of free-floating asteroids in an asteroid field. Notice how there are no grid lines, no zero coordinates, no origin. Anytime you find grid lines, you can rest assured that you're looking at a human-constructed coordinate system. Nature never creates grid lines of any sort, and no such systems exist in nature. We only construct grids because they're simple enough for us to comprehend, and they make communication easier. What we really mean by 3 dimensions of space is really that we need 3 dimensions at a minimum in order to say everything that we need to say about a location. The ratios between the lengths of these lines and the angles between the lines are all invariant properties, which is why I say that these are real properties of nature. These objective features are all independent of how we decide to orient, scale, and position our coordinate system in velocity space. All of these properties remain the same no matter what we consider to be stationary, and no matter how fast or in which direction an observer happens to be moving. Pythagorean theorem also works in velocity space. In fact, all of the rules that you may have learned for how to find angles and distances in trigonometry work just as well in velocity space as they do in ordinary space. And the reason that these same rules work in velocity space is that velocity space is every bit as real as space is. It's almost as though there have always been 2 spaces, and velocity space is the space that has always been ignored. But ignoring the existence of a coherent and objectively real velocity space comes with dire consequences. In special relativity, the observer's location in velocity space must always be at the origin of a coordinate system. In other words, an observer must always be considered to be stationary from their own default perspective, and this is a really bad idea. All speeds are then construed as relative to a specific observer, and this causes confusion between relativity and subjectivity, making certain objective features of reality appear to be dependent on a mere subjective perspective. Let's now review what Galilean relativity implies about the nature of speed and velocity. Number 1. A speed is never a property of an object or of an observer. Number 2. A speed is always a relationship between 2 points in velocity space. Number 3. A speed is a straight line connecting 2 points in velocity space. Number 4. A speed is symmetric because the speed of object A relative to object B is equal to the speed of object B relative to object A. Number 5. A speed between 2 objects is independent from whatever is considered to be stationary. Number 6. A speed between 2 objects is independent of where the observer is in velocity space. And number 7. The location of the observer in velocity space is independent from what is considered to be stationary. All distances in velocity space are relative because all distances in space are also relative. Both Galileo and Newton understood perfectly well that velocity space is analogous to ordinary space, and that distances and angles in velocity space work in exactly the same way as distances and angles in space do. The idea that no object really has any particular velocity leads to the idea that there is no such thing as a stationary inertial frame of reference, which in turn leads to the idea that Earth is not stationary. And if Earth is not stationary, then it is just as valid to conclude that Earth revolves around the Sun as it is to reach the opposite conclusion. In fact, the idea that Earth revolves around the Sun turned out to be a much more elegant idea than the one that was preferred by the scientific establishment of Galileo's day. Even though all of this was understood 5 centuries ago, somehow we have allowed this vast treasure trove of wisdom to be forgotten relatively recently. And in the void of ignorance, all sorts of flimsy and absurd ideas have taken up residence. According to special relativity, a speed is not only relative, but also subjective, as it is merely a matter of perspective, as are all measures of time or space. Here are a few examples of how time, space, and speed are all regarded as mere appearances with no real depth in special relativity. Time dilation. What is 10 minutes for one observer could be 2 minutes for another observer. Length contraction. What is 10 meters for one observer could be 2 meters for another observer. Symmetry. While observer A accurately believes that observer B's time has slowed down relative to theirs, observer B also accurately believes that observer A's time has slowed down relative to theirs. The speed of light. The one-way speed of light is understood as both immeasurable and meaningless according to special relativity. And so when we say the speed of light, what we really mean is the averaged two-way speed of light. Simultaneity. 2 clocks cannot be synchronized simultaneously in all inertial frames of reference, and so there can be no such thing as what time it really is. There can be no universal or global time. The problem that I've encountered quite regularly is that the idea that time, space, and speed are all mere appearances or perspectives has been piggybacking on the idea that all motion is relative. The idea that all motion is relative is actually being used as an ink cloud to confuse and disorient people to the point where they can accept these extraordinarily shallow and incoherent notions of time, space, and speed. This is why it is so important to make it clear that both a speed and a location in velocity space can be, at the same time, objectively true and also relative. There really is a pervasive anything goes mentality amongst physicists, and this mentality makes the incoherence and contradiction that is inherent in special relativity tolerable. I think that the cure for this complacency is to fully appreciate how the points themselves can mutually define and determine their own locations, with the idea of an endogenous coordinate system. The invariant properties that exist are more than sufficient for establishing a reality that is both objective and coherent. In summary, Galileo was the first to propose that all motion is relative. And what it really means to say that all motion is relative is to say that speed is a distance between points in a three-dimensional velocity space, and that each point in velocity space may be regarded as a particular inertial frame of reference. If you understand this, then you necessarily understand what relativity really means, and you also understand what velocity space is. As difficult as it is to believe, and as difficult as it is to remember, the truth is that you are actually moving in all directions and at all speeds simultaneously right now. You are also not moving at any particular speed or in any particular direction. And you are not stationary either. Rather, stationary is but one of your many velocities. It is also important to bear in mind that space itself rests on a foundation of velocity space. This is demonstrably true because before you can construct any spatial coordinate system, you must first choose a particular location in velocity space in which and with which to anchor your spatial coordinate system. I say this because a spatial coordinate system cannot be considered to be moving within itself. That would not make any sense. So of course, any coordinate system must be regarded as stationary within its own implied inertial frame of reference. Galileo really deserves the bulk of the credit for discovering velocity space, but there were other important contributions as well. Sir Isaac Newton and the law of inertial motion. Isaac Newton was the first to propose that all objects have an inherent tendency to remain in the same fixed position in velocity space, unless acted upon by some external force. This is known as Newton's first law of motion, and it describes what we call inertia. This is also where we get the idea of an inertial frame of reference. What it really means to be in inertial motion is to be frozen in velocity space. So if you are in a fixed location in velocity space, then this means that you are moving at a constant speed and in a straight line. In other words, you are not accelerating or decelerating, and you are not moving along a curved path. One can ask, what is causing every object in the universe to be held in a fixed location in velocity space by default? Is there some invisible glue? Why and how does the universe keep track of where everything is in velocity space? But such questions are probably beyond the scope of science at this time, and it doesn't seem likely that we will obtain satisfactory answers anytime soon. We just need to accept that it is the way it is. This is how the universe works. In order for our location in velocity space to change, some force must act upon us. Albert Einstein and the invariant speed of light. Albert Einstein is famous for the idea that the speed of light is constant relative to the observer, but not relative to the source of the light. In other words, light is always observed to be the same distance away from the observer in velocity space, no matter where the observer is in velocity space. This is known as special relativity, which began as a theory about the behavior of light. The apparently invariant speed of light presents us with an additional parallel between velocity space and space. Because speed is nothing more than the distance between 2 points in velocity space, if we have an observer at one point in velocity space, then all of the light that this particular observer can see must occupy a spherical bubble shape in velocity space with a radius that is equal to the speed of light. The observer would then have to be at the center of this light bubble at all times. What this tells us is that not only does the light that we can and can't see change as we move from location to location in space, but the light that we can and can't see also changes as we move from location to location in velocity space, because we also drag our light bubble along with us in velocity space. Our location in velocity space has gained a new significance because we can now see that it determines which light we can and can't see. I should add that this was already known prior to Einstein following the results of the Michelson-Morley experiment in 1887 and the implications of Maxwell's equations. But Einstein was the first to fully embrace this idea and run with it, pursuing it to what were, at the time, thought to be its logical conclusions, with the help of a few now famous thought experiments, namely the rigid rod thought experiment and the light clock thought experiment. However, Einstein also ran with this idea in the wrong direction, and if he had had the benefit of hindsight, he probably would have taken this idea in an entirely different direction. The missing piece of the puzzle, which Einstein did not have in 1905, would later be introduced by Werner Heisenberg and his contribution to the Copenhagen interpretation of quantum mechanics. Werner Heisenberg and the uncertainty principle. Werner Heisenberg was the first to propose that the more defined a location of a particle, such as an electron, is in velocity space, the less well-defined the location of that same particle is in space, and similarly, that the more well-defined a particle's location is in space, the less sharply defined that same particle's location is in velocity space. This principle is called the Heisenberg uncertainty principle, and this is a theory about the limits of our knowledge about the simultaneous position and velocity of a particle. In other words, there's a strange connection and an equivalence between space and velocity space, and this connection is still deeply mysterious. What I have done here is I have combined the insights of all four of these brilliant minds, and I've arrived at the conclusion that velocity space constitutes 3 of the 7 basic dimensions of reality. Once again, there are 3 dimensions of space, 1 dimension of time, and 3 dimensions of velocity space. With Galileo's insight, we now know that what we call space is actually grounded in velocity space, and that a speed is really a distance between 2 points in velocity space. With Isaac Newton's insight, we now know that all objects passively maintain a fixed position in velocity space. With Einstein's insight in mind, we can see that the light that we interact with not only depends on where the observer is in space, but also where the observer is in velocity space. With Heisenberg's insight in mind, we can see that the 3 dimensions of space and the 3 dimensions of velocity space are fundamentally equivalent and interchangeable. The more closely we examine velocity space, the less closely we examine space, and vice versa. Any spatial coordinate system that we construct must itself have a specific location in velocity space. In other words, just having a spatial coordinate system demands that we designate some location in velocity space as stationary, meaning that space itself is not fundamental, as space itself rests on a foundation of velocity space. However, even though space does rest on a foundation of velocity space also rests on a foundation of space, because in order to calculate a velocity, one needs to have both a distance in space and a distance in time. These 3 types of dimensions are each mutually interdependent. Speed, direction, time, and space are conceptually inseparable. In other words, space rests upon velocity space, and velocity space rests upon space. Neither space nor velocity space are more foundational than the other. The 3 dimensions of space are orthogonal or independent from one another, and the 3 dimensions of velocity space are also orthogonal or independent from one another. But the 7 dimensions of reality are not orthogonal or independent in exactly the same sense. You can take your finger and point in any one of an infinite number of directions, and we can apply an arbitrary classification system to the direction that you're pointing in. Let's say that you're on Earth and you're pointing towards the star that we call Deneb. What you're doing is pointing in a particular direction. This direction that you're pointing in has meaning in both space and velocity space. The difference between space and velocity space is that the magnitude of a vector has a very different meaning in one versus the other. Of course, we don't need to make our system for describing directions the same for both space and velocity space. But because we can use the same system, we should, just for the sake of elegance and coherence. A circle has 360 degrees, but whether we are talking about the number of degrees or the number of tiles on the surface of a sphere, we are merely describing an arbitrary convention that has no physical meaning. In reality, there are an infinite number of distinct directions that one could point in, because there are an infinite number of points on the surface of a sphere. Deneb is an object that I like to use because even though it is about 100 million times as far away from Earth as the Sun is, it is still prominent in the sky and easily visible to the naked eye, because it is such an extremely bright star. Extremely distant and bright stars, such as Deneb, can serve as an ideal, point-like anchor for a directional coordinate system. I am now convinced that velocity space is every bit as real, important, and fundamental as space and time are. But I should also acknowledge that my mind is somewhat unique. For some reason, I have an innate ability to visualize how everything looks in velocity space. To me, everything about velocity space is intuitive and immediately obvious. I don't have to think about any of it. I also don't need to do any explicit mathematical operations in order to gain insight into velocity space. But I realize that most people don't have such a strong intuitive grasp of velocity space. As a result, people will often ask me to show them my work and to show them my calculations. This demand is somewhat naive and unrealistic, because I don't rely on any equations myself. To close this video, I just want to leave you with one thought-provoking question. If a photon is moving at the speed of light relative to me, then at what speed am I moving at relative to the photon?